Okay, hello. Welcome to our fourth lecture on Fourier methods in combinatorial number theory. So I'm Sean Prendeville. Just so you're aware, this is being recorded. So any contribution you make during the talk will be recorded as well. And make sure you're happy with that before you contribute. I really hope that doesn't inhibit questions. We've had some great questions in previous weeks. So please do continue to unmute yourself and ask a question, or use the raise your hand feature, or put a question in the chat. I might not monitor the chat as regularly as I'd like to, but I'll try to. If anyone's got any accessibility issues with the notes or the videos or the slides, do let me know and we'll try and resolve those. The notes for the course are available on the course webpage. They're linked to in the YouTube description for this course. And I'm going to put all the details into the notes, and your comments and clarifications on the notes are greatly appreciated. In the lectures, I'm going to be a bit more hand-wavy with the details, and I hope you'll give me license to do that. Okay, so today what we're going to talk about, we're talking about the transference principle. So what is the transference principle there for? Excuse me. It's to deal with a problem of sparsity. So far, we've been interested in solving equations, linear equations, in dense sets of integers. And we've managed to do that in a few examples. But the thing is, all of those sets are dense. We solved equations in dense sets of integers, and these were translation invariant equations. What do you do with sparse sets? So we'll see there's a limit to how sparse you can take a set before you can start proving results about, thank you, I need to start recording this. So that is a good message to have received. So now we're recording. Okay. So let me recap and get my train of thought back together. We've worked with dense sets of integers. We're interested in sparse sets of integers. The primes are an example of a sparse set of integers. The squares are an example of a sparse set of integers. And unfortunately, we can't hope to show that sets of squares or sets of primes, or sets of squares at least, contain solutions to certain equations on density grounds alone. They're just too sparse. But you might hope that you can prove a theorem about sets of squares which are relatively dense within the squares. So the machinery we'll discuss, which allows one to prove these kind of results, is the transference principle. And I'm going to give an example of this transference principle in the simplest instance I could think of, with the least technicalities, requiring the least amount of background. And that's to prove a result about SID-on sets. Don't worry if you haven't met a SID-on set before, we'll introduce them. And we'll show that SID-on sets are sparse. That if you're a large SID-on set, you're within a positive proportion of the maximum size you can have, then these large SID-on sets have solutions to certain linear equations. So that's a result about sparse sets of integers. And we're solving an equation in that sparse sets of integers. Our previous methods won't apply to this level of sparsity, so we need to develop some new tools, and that tool will be the transference principle. So why is sparsity a problem? So we've already shown in lecture 2 that dense sets of integers contain 3-term progressions. That's Roth theorem. And last lecture, using arithmetic regularity, we actually counted solutions to this equation in 5 variables in a dense set of integers. And we showed that there's a positive proportion of the total number of solutions in the interval come from a dense set, from any dense set you want. That's great. But what about sparse sets? And what do I mean by sparse? I mean a set which the proportion it takes up in the interval decays as the length of the interval increases. So it doesn't take up a positive proportion of the interval for large intervals. An example would be the primes. They have logarithmic density, 1 over log n. That tends to 0 as n tends to infinity. And can we conclude that the primes contain 3-term progressions or solutions to our 5-variable equation purely using their density. And it's a remarkable achievement of Bloom-Sisask and Schoen-Sisask that you can. This result of Schoen and Sisask predates the work of Bloom and Sisask and actually applies for equations in 4 or more variables. So it seems like the methods we've developed, if one can refine them considerably and be very careful, and that's what these works do, along with a host of other ideas, but they managed to get a lot of these techniques developed for dense sets of integers to work in this regime, this regime of sparsity. That's a fantastic achievement. Can you go even sparser? Can you go polynomially sparse, where your density is some kind of polynomial function of the length of the interval? Maybe you take a root of the length of the interval, or n to the 2/3, where n is the length of the interval. Or maybe you just, the cardinality of your set is small. There's some power saving compared to the length of the interval, but it's a small power saving. Can our methods tolerate this level of sparsity? Definitely not is the answer. And the reason is there's a construction of Berend from the 40s of a set of integers which is better than polynomial in its sparsity. It's larger than any power of the length of the interval, any power which is less than 1, asymptotically. And it doesn't have any 3-term progressions, and it doesn't have any non-trivial solutions to our equation in 5 variables. So we can't hope to deal with this level of sparsity in general. But what about if you're contained in some particularly nice sparse set? So the Berend set is a bad sparse set, but some sparse sets might be nicer than others. And you might hope that if you're in some ambient sparse set S, and you take a subset of that ambient sparse set, and it's dense relative to the ambient set S, takes up a positive proportion of the set S, then you can solve an equation in this relatively dense set. So this isn't a theorem, this is sort of a hoped for theorem, a relative Roth theorem. So can one come up with sets S, sparse sets, for which this is true? Now, definitely the primes work. We didn't really need any information about the primes. You could just take a set of the same density as the primes, and this relative Roth theorem would hold for a set of logarithmic density. But actually, this kind of relative Roth theorem predates the work of Bloom-Sisask. So we knew that before the work of Bloom-Sisask, that the primes are a good host set, and relatively dense subsets of the primes contain non-trivial solutions to this equation. So you can prove a relative Roth theorem for the primes. You can't hope to prove a relative Roth theorem for the Berend set because the Berend set itself lacks solutions, non-trivial solutions to this equation. That's bad news. Some good news is you can go very sparse if your host set is random. So if you take a random subset of this interval whose cardinality is root of the length of the interval, then almost surely a relative Roth theorem does hold for this random host set. And in fact, I think n to the 1/2 is quite a crude bound here, and one can tolerate much smaller random sets, something which is maybe significantly larger than n to the 1/4, I think. Okay. So random sets are good host sets for relative Roth theorems. And the squares are a good host set for this form of the relative Roth theorem, where we're looking for solutions to this equation in 5 or more variables. And what we're going to look at today is Sidon sets. Sidon sets which are within a positive proportion of the largest size they can be. So the largest size the SID-on set can have is n to the 1/2 if it's contained in the interval 1 up to m. And today we'll show that SID-on sets are good candidates for this relative Roth theorem. And as I said before, that basically, wherever there's a check mark, here, we're using the transference principle to deduce these results. So all these results go via the same machinery, or one can prove them using this transference technology. And my feeling is that this SID-on example is the simplest, the technically simplest example, and that's the reason I'm discussing it today. It requires the least amount of number theory. Okay. So how does this transference principle go? So it goes by taking your sparse set, your subset, which is relatively dense in some ambient sparse set, and then cooking up a dense set of integers which models your sparse set. So here's the setup. We've got our host set S, our dense subset of our host set A. Everything lies in this interval 1 up to n. And we'll prove a dense model lemma in that we'll cook up some dense set A tilde. It's definitely dense. And it models the sparse set because the Fourier transform of the sparse set resembles the Fourier transform of the dense set. And this approximation is going to be in the L infinity norm, so it's pointwise. Fourier transforms resemble each other pointwise. Now, because this is a sparse Fourier transform and this is a dense Fourier transform, the order of magnitude of these two transforms, on average, it's definitely a different order of magnitude, simply because the sets have a different order of magnitude. So you can't hope for a pointwise approximation without some rescaling. And the amount we're rescaling by is the density of our host set S. And that's the right rescaling with our conventions for how we've normalized Fourier transforms. Okay. So that's what we want to do. And why is that useful? Well, we know by orthogonality, the number of solutions to our equation in a set A, you can describe that in terms of a Fourier integral, an integral of Fourier transforms. So the Fourier transform completely determines the number of solutions to an equation in your set. So if two Fourier transforms resemble each other pointwise, then their count of solutions are going to resemble each other, one would hope. So this Fourier transform resembles the Fourier transform of our dense set with some scaling factor. And now we know how to analyze this Fourier integral because we can re-relate it back to a count of solutions to a certain linear equation with variables this time coming from a dense set. And we know that this translation invariant equation has many solutions in any dense set. It's got around at least n to the 4 solutions in any dense set. That's what we proved last time. Okay. So by invoking this result about dense sets of integers and using this dense model for our sparse set, we've obtained a lower bound from the number of solutions to our linear equation in our sparse set, and it has this shape. And if you divide through by powers of n, your eventual lower bound is of this form. And just to remark, this is the order of magnitude you would expect from the naive heuristic, which we established in lecture 1. Okay, so there's lots of solutions to the equation in this sparse set. So that's great. In particular, if one did some elementary counting arguments, you could show there's at least one non-trivial solution in your sparse set. Those elementary counting arguments require that your host set really isn't very, very sparse. But in our applications, it's not going to be, and one can show using this counting argument that there exists at least one non-trivial solution. So that's what we hope to do. We hope to model our sparse set with a dense set. And in the remainder of this lecture, I'm just going to enact how to do this for these dense Sidon sets. But let's talk about what a Sidon set is first. So a Sidon set is a set whose representation function, if we're trying to represent integers n as a difference of two elements of our set S, a set is Sidon if this representation function is as small as it can be. It's at most 1. It's as small as it can be everywhere apart from at the integer 0, because when n is 0, you actually get quite a lot of representations by just setting x equal to y. You get at least s representations. But away from 0, this number of representations of an integer as a difference of elements in our set S is as small as it can be. It's at most 1. And you can show that Sidon sets, their order of magnitude is at most square root of the size of the interval. So they're genuinely sparse sets, polynomially sparse. They're very sparse. So I give the argument, or a argument for this in the notes. And this upper bound is actually sharp. You can construct a Sidon set whose cardinality is up to lower order terms square root of the length of the interval. That's also given in the notes. Okay, so these are genuinely sparse sets, and they can take this order of magnitude n to the half. So rather than focusing on these bounds here, what I want to do is prove a combinatorial theorem within Sidon sets. So I take a Sidon set, and I assume it's a positive proportion of the maximum possible size it can be. So it's a delta proportion of the maximum size it can take. And my conclusion is the number of solutions to this translation invariant equation in 5 variables, with variables constrained to my dense Sidon set, is n to the 3/2 with some implicit constant depending on the density. And just to say, this order of magnitude here is that given by the naive heuristic. So these dense Sidon sets contain lots of solutions to a translation invariant equation in 5 variables. You can modify coefficients provided you've still got a translation invariant equation. You can look at equations in more than 5 variables, again, provided it's translation invariant. What you can't do is go to equations in less variables, because there are equations in 4 variables and less variables where the only solutions in a Sidon set are trivial. And that really comes down to the defining property of a Sidon set. So it's a nice exercise to construct these bad equations. So it's sort of weird that Sidon sets actually have very few solutions to lots of equations in 4 or less variables. But as soon as you get to 5 or more variables, they've got plenty of solutions. But this is what we're going to prove today, using this transference principle. So there's a question about, in the definition of Sidon set, you can change you can replace 1 with other numbers. Yeah, that's fine. Maybe one could try getting these methods to work for those sets. So how do we model a dense Sidon set with a dense set? So what we're going to do is we're going to take a Sidon set. We don't necessarily know it's dense or dense Sidon. It's not necessarily a positive proportion of square root n in size. And what we're going to show is we're going to cook up a function, a non-negative function, which is going to be an analytic proxy for the indicator function of a dense set. So that's a bit of a mouthful. What do I mean by that? So as a first approximation, you can just think of this function f as the indicator function of a dense set. It's not that. It's a more general thing, but it behaves like the indicator function of a dense set. So why does it behave like the indicator function of a dense set? Well, its L2 norm is like the L2 norm of an indicator function. So if you looked at the L2 norm of an indicator function, this is essentially the cardinality of the set. And if your subset is contained in the interval, this is at most n. So our proxy behaves in a similar manner. And why is it a dense model for our SID-on set? Well, its Fourier transform resembles a rescaled version of the Fourier transform of our SID-on set, up to some epsilon error. Okay. Now, where does epsilon come from? As I've stated it, you could take epsilon to be arbitrarily small, and you essentially get an equality here. So something can go wrong, and epsilon is bounded in terms of the length of the interval. So if you want a very small epsilon, you have to take a very long interval. So this is our dense model for SID-on sets. So let's talk about how we're going to prove this. So I basically want to, before just giving the kind of the explicit definition of f, I could just write that down straight away, and it's not very informative. I want to sort of motivate where this construction comes from. So our first guess is just to take a weighted indicator function of the SID-on set. Why have I weighted with square root n? And that's because I want a function whose L1 norm is dense, in that if I sum over all values in the interval, I get a positive proportion of the interval. And because our SID-on set has size around n to the half is a good weighting to get something which looks like a dense function. But this is a really bad choice. So what does this look like? We've got some SID-on set. It's a sparse set of points in our interval. And with this scaling, I've got some massive point masses at each of these integers. And these have height n to the half. And this definitely doesn't behave like a bounded function, because its mass is too concentrated. So its L2 norm, or the square of its L2 norm, is n to the 3/2, which is much larger than the L2 norm of a bounded function, or the characteristic function of a set. So this is a bad first guess. Now maybe your second guess is to average the function. Maybe you just smooth out all of these peaks and then just take the average of your function. So this function would be the average of our rescaled SID-on set times the indicator function of our interval. So that's good in terms of L2 boundedness. You can check that this smoothed out average, the indicator function of our interval appropriately weighted, that definitely has L2 boundedness. But the problem is, its Fourier transform is nothing like the Fourier transform of the original set. So why is that? Well, if you remember, the Fourier transform of an interval outside of a small neighborhood of the zero frequency, the Fourier transform of the interval is small everywhere, outside of a very small neighborhood of the zero frequency. But you can have a dense SID-on set which consists only of odd numbers. And it's worth having a think about how to construct that. So a dense SID-on set can consist solely of odd numbers or solely of even numbers. So you can have a SID-on set which has a very large Fourier transform at the frequency 1/2. And the Fourier transform of the interval has a very small frequency, very small Fourier transform at the frequency 1/2. So you definitely don't get this Fourier indistinguishability by just averaging your function. So there's a tension here. We're going to basically find a midpoint between these two constructions. We're going to average locally on some subregions, and that will give us L2 boundedness. But we also need to average in such a way that we still have this Fourier approximation. So Zoe asks, is the L2 bound involved in all transference principle setups? No. So actually, we could work harder and have a generally bounded approximant if we wanted to. It could be L infinity bounded. We could get an LP bounded function. Any of these things would work. But for Sidon sets, this is the easiest to prove. Okay. So yeah, this first guess is bad. It's got a bad L2 norm. So in order to mop up all this kind of Fourier behavior, we need the transform of our proxy to really quite accurately resemble the transform, the rescaled transform of our set. Whenever the set, the Sidon set, has a large Fourier transform. And what do I mean by large? I mean a positive proportion of its maximum possible size. I mean, even if this is half the size of this, because this part is large, because the rescaled transform of the Sidon set is large, just being half the size still gives you a very large difference. So what I'm trying to emphasize is, when the Sidon set has a large frequency, your dense model has to really accurately model and account for that large frequency. But when the Sidon set has a small frequency, a frequency at which it's small, you care less about the size of the dense model. As long as it's somewhat small, we can beat this bound. Okay. So again, this is me just trying to motivate the construction that's coming. So I want to informally define a concept of the spectrum, or the large spectrum of our Sidon set. It's the set of frequencies where we get a large Fourier transform, where the Fourier transform is a positive proportion of its maximum possible size. We'll define this more concretely in the next slide. So we definitely need the Fourier transform of our model to look like this product of three functions, the rescaled Fourier transform of our Sidon set times the indicator function of this large spectrum. We need this to hold on the spectrum. Okay. And what we're going to do is try and construct a function g, trying to construct a function g on the integers whose Fourier transform resembles this indicator function of the spectrum. So why is that good? Well, if you have a product of two functions on frequency space, you might hope to come up with a function in physical space whose Fourier transform resembles that product using this convolution identity that some of you will be familiar with. And it says the Fourier transform of a convolution defined in this manner is equal to the product of the Fourier transforms. That's a simple exercise to check. And here I've defined convolution as the number of representations of an integer x occurring in my convolution as a sum of two elements where each element is weighted by its corresponding function. Okay. So if we're trying to pick up this behavior, we're going to try and come up with a function whose Fourier transform resembles this product. And the way we'll do that is come up with a function in physical space whose Fourier transform resembles the indicator function of the large spectrum. And actually, the function g we're going to come up with, so given this, one might take f to be this rescaled this rescaled indicator function of our Sidon set convolved with this set g. this function g. And it'll turn out that we can actually take g to be some rescaled indicator function of a set. So hopefully I've waved my hands enough for you to be willing to accept this motivation. And let's just get into the concrete details. So let's define the spectrum more properly. It might be hard to parse this on first reading. It's just a set of frequencies where our Fourier transform is eta large. Don't worry too much about this definition of B. It's a Bohr set, and you'll see why this is a good choice of sets shortly. So don't try and parse this too hard at the moment. It's the set of integers in this sort of short interval, eta short interval, such that when you multiply n by a frequency coming from the large spectrum, you're approximately equal to 0 mod 1. So we'll see why that's useful. So we're going to take G. This is our first attempt at a dense model for our SID-on set S. We're going to convolve our SID-on set with this Bohr set, appropriately rescaled. And by the convolution identity, the Fourier transform of G is a product of Fourier transforms of the individual functions. So when we compare the Fourier transform of our SID-on set with the Fourier transform of G, we can factor out the Fourier transform of our SID-on set. And just to say that this number here is equal to the, with our convention and normalizations, it's equal to the cardinality of the set B. So when you divide by the cardinality of B, you get 1 here. That accounts for this part. And this presence of this Fourier transform of B here is coming from the convolution formula. Okay. So let's show that this is small at all frequencies. When we're in the spectrum, when we're outside of the large spectrum, our Fourier transform is small of our SID-on set. So this is small. So in that situation, because we can bound this by the triangle inequality, it's at most 2. When we divide through by the size of the set B, we get a bound which is of order of magnitude eta times S. The size of the SID-on set is the maximum possible this could be. Okay. So that's when we're outside of the large spectrum. When we're in the spectrum, well, this is where our Bohr set comes in useful. This part is going to be large because we're in the large spectrum. So we're hoping this part is small. Now, if you lie in the Bohr set and your frequency comes from the spectrum, because this n to the alpha is approximately 0 mod 1, when n is in the Bohr set and alpha is in the spectrum, the phase evaluated at alpha n is approximately 1. Okay, so let's sum over all elements in the Bohr set, and we see that the Fourier transform of our Bohr set, evaluated at the frequency alpha, is approximately equal to the Fourier transform of the Bohr set at the trivial frequency 0. So when alpha is in the large spectrum, this function here resembles this constant, in that their difference is an eta proportion of the size of the Bohr set. So you substitute this bound into here, and you get eta times the size of the SID-on set again. So we've got a uniform bound for the difference between the Fourier transform of G and the Fourier transform of our SID-on set. That's great. So why is this function L2 bounded? So let me just recall what this definition of G is. It's the convolution of the SID-on set with this Bohr set rescaled. And we've got this nice error term. This error in our Fourier approximation is eta of the size of the SID-on set, which is about root n. Now we're going to define f, our dense model, as a rescaled version of this function g. With that rescaling, we get that n to the 1/2 times the Fourier transform of s minus f hat in the L infinity norm. This is at most eta times n. So we've got the closeness in the L infinity Fourier norm. So why does this have a bounded L2 norm, or why is its L2 norm behave like the L2 norm of a characteristic function of a set? So let's calculate its L2 norm, or estimate its L2 norm. You substitute the definition of f, square it, and sum over all possible integers. You get some factor here, which comes from our scalings. We've scaled by n to the 1/2 inside the square, and 2 copies of the cardinality of our Bohr set on the denominator. And once you've accounted for that rescaling, because we're calculating the L2 norm of a convolution, the L2 norm of a convolution is like counting solutions to an equation in 4 variables. And it's this equation. So a little thought will show you that the L2 norm of a convolution is like counting solutions to this equation in 4 variables, where the n variables come from our Sidon set and the m variables come from our Bohr set. Now, what are we aiming to show? We're aiming to show that this is of order of magnitude n. So that means we want this to be of order of magnitude the Bohr set squared, because then this order of magnitude cancels with our denominator and we're left with n. So why is the order of magnitude of this count of solutions to a certain linear equation in 4 variables at most the order of the Bohr set squared? Well, you sum over the m variables coming from the Bohr set, and then we're counting representations of this difference, m1 minus m2. We're counting representations as a difference of elements in our Sidon set. And we know this is as small as it can be because we're in a Sidon set. So using the defining property of Sidon sets, we can bound this by 1, at least when m1 is not equal to m2. There's a different contribution coming from that, that diagonal situation in which m1 is equal to m2. Let's not worry too much about it. You can account for it. But you can see that for most values of m1 and m2, which are distinct, this is going to be at most 1. And so you get an upper bound of b squared for this inner sum. And that gives you your order of magnitude for your L2 norm. So we rescaled g and we got a function with bounded L2 norm. And our construction of g ensures that the Fourier transform of f resembles the rescaled Fourier transform of our Sidon set. So let's recap. We've got a Sidon set. We've got this function f, which is a proxy for a dense set of integers or a bounded function. Its L2 norm behaves as if it's bounded. The Fourier transform of f resembles the Fourier transform of the Sidon set. So why is that useful? Well, if our set is a dense Sidon set, it's a delta proportion of its maximum possible size, then I want to show that this dense model is also a dense function, i.e., so eta, good question. What do we end up setting eta to be? Some small power of, some small fraction of epsilon. In the notes, I work a little bit harder to get some nicer properties of this. So perhaps one's first guess gives you a function which isn't defined on this interval, but on a slightly wider interval. But you can sort of mop up these boundary points and get a function defined on the original interval we worked with. And the cost for that is I have to have an eta, which is a square root of the epsilon parameter I'm aiming for. All of this is in the technicalities, which I'm just sweeping under the carpet. But yeah, if you're interested in where eta comes from and where epsilon comes from, do check the notes out. Okay. So if I started with a dense Sidon set, I want to show that this function is dense in that its L1 norm is a positive proportion of n, which would be the estimate for a dense set. How do I do that? Well, the sum of this function is the trivial Fourier coefficient. And the trivial Fourier coefficient resembles the trivial Fourier coefficient of my Sidon set. And the trivial Fourier coefficient of the Sidon set takes this size. So I do have a dense function. So when we have a function with bounded L2 norm and dense L1 norm, we can count many solutions to our equation weighted by this function. So I'm claiming that's the case. So last time we proved this when f is equal to the indicator function of a dense set. And in that situation, this first condition is automatic. And this second condition is just saying that this set A is dense, delta dense. But you can relax. So analytically, the argument doesn't really care if we're working with an indicator function of a dense set or just a dense function with bounded L2 norm. And so you can deduce this result about functions with bounded L2 norm from the result about dense sets of integers by just thresholding. So you can definitely bound your function below by this, this level set function with some sort of fudge factor, half delta. So that bound is definitely true. And because this function has bounded L2 norm, you can show that this is a dense set of integers. So you can bound this function f by the indicator function. You can bound it below by the indicator function of a dense set with some fudge factor. So to prove this L2 version of Roth's theorem, we just invoke our counting version of Roth's theorem in many variables that we proved last time for this equation. You apply it to this set, and you use this lower bound to obtain your lower bound for the solution count for f. So there's not too much going on there, it's just thresholding. So things are good, right? We've got this dense model whose Fourier transform resembles the Fourier transform of our Sidon set, and the dense model counts many solutions to our equation. So it seems like the only thing we need to do now is to establish that this count for the dense model is similar to the analogous count for the Sidon set. So we'll do that in this Fourier control lemma. We've got two functions on the interval 1 up to n, and we'll assume they're somewhat bounded. And what do I mean by bounded? I mean that it looks kind of technical when you first see it, but I'm assuming the L4 norm of their Fourier transform is comparable to the L4 norm of the Fourier transform of the interval. And just to say, this number is n to the 3/4, or at most n to the 3/4, if you're interested. Don't worry about this too much for now. Let me just state the result. So two functions whose Fourier transform is comparable have similar solution counts up to some error measured by the difference in their Fourier transforms. So this is a very similar result to, I think, a result we've employed in different variants in the first 3 lectures. And it's essentially telescoping to compare these two counts, plus the orthogonality relations to write things in terms of a Fourier integral, plus Holder's inequality, to extract an L infinity Fourier norm. So we've seen this argument many times, but unlike previous instances where we worked with bounded functions, functions whose absolute value was bounded pointwise in terms of 1, now we've got this weaker notion of boundedness. But this is good enough. And this is essentially coming from our application of Holder's inequality in Fourier space. So I wouldn't worry too much about it. It looks technical. If you tried to prove it, you could prove it using telescoping orthogonality and Holder. If you'll allow me, just hopefully buy this for now, that this is okay. But what I'd say is for our application, we're working with a rescaled Sidon set, and we're working with a function with bounded L2 norm. So we need to verify that both our rescaled Sidon set and our function with bounded L2 norm have a Fourier transform which is comparable to that, at least in the L4 norm of the interval. So how does that go? So let me do it for the Sidon set. So, yeah. The rescaled Fourier transform of the Sidon set, its fourth moment to the power 4 is a Fourier integral. It's just n squared times a Fourier integral of the Sidon set to the power 4. And by orthogonality, this is just n squared times the number of solutions to an equation in 4 variables weighted by the Sidon set. Okay. And it's a trick we've already seen before. Supposing if we sum over y and y prime, provided y and y prime are distinct, there's at most one representation of y minus y prime as x minus x prime. Now you also have to account for the diagonal contribution when y is equal to y prime. Let's not worry too much about that. But you can sort of take it on trust that you get a bound of the form n squared s squared, which is the number of choices for pairs y and y prime. For each pair of y and y prime, we get one representation as x minus x prime. So this is about the right order of magnitude. And as we're working with the Sidon set, it has cardinality at most square root n. So this is of order of magnitude n to the 3. And that's the right order of magnitude for the L4 norm of the Fourier transform of the interval. And if you've got a function with bounded L2 norm, like our dense model, you can mess around with Holder's inequality and Parseval's inequality to also show that that satisfies this hypothesis. Okay. So the upshot of all of this is that the solution count for our dense model is comparable to the solution count from our rescaled Fourier transform. So let's put everything together. We've got a Sidon set. It's dense as a Sidon set. It takes up a delta proportion of the maximum possible size. We construct a dense model, a function with L2 norm behaving like the L2 norm of an indicator function, which is Fourier indistinguishable from our rescaled Sidon set. Their solution counts are comparable by the Fourier control lemma. Once you've got this rescaling coming from this factor here. And we know the right-hand side is large by our L2 variant of Roth's theorem, which is really just a tweak of our counting version of Roth's theorem in many variables. So because the right-hand side is large, the left-hand side is large, and after you divide through by this scaling factor, you get many solutions to your equation in your Sidon set with some implicit constant coming from the density. And just to emphasize, this is the order of magnitude of the Sidon set to the power 5 divided by the length of the interval, which is the count you'd expect from the naive heuristic. Okay, so that's an example of the transference principle. And the details, which I've been pretty sketchy about today, are elaborated in the notes. Great. So now what we're going to look at next time. Well, so far, we've used again and again this Fourier control lemma. If we want to count solutions, the number of configurations in our set, could be sparse, it could be dense, we do that by rewriting the number of solutions or the number of configurations in terms of a Fourier integral. And that's been super useful. We've used it 4 times. Unfortunately, there are configurations, linear configurations, nonlinear configurations, where the Fourier integral, not only is it not useful or doesn't appear to be useful, you can prove it's not useful. So one example is 4-term progressions. So you can encode a 4-term progression as a solution of a system of 2 simultaneous linear equations. And you can certainly encode that number of solutions, the solution count for the system of equations, as a 2-dimensional Fourier integral. So an integral of Fourier transforms with respect to some 2-dimensional torus. But it seems very hard to use that Fourier integral. And in fact, you can show that that's provably a bad thing to do, because that Fourier integral only picks up sort of correlations of your set with linear phases. And if you want to count the number of 4-term progressions in the set, you have to account for quadratic phases and higher order phases, whatever that means. So the Fourier integral is provably useless for some configurations. Here's another configuration which the Fourier integral doesn't look that useful for when you try and attack it. So it looks like a 3-term progression from Roth's theorem, but instead of taking 2 times the differencing parameter in the final point of the configuration, you square the differencing parameter. And again, it's hard to see how to get a Fourier integral to be useful for this. Even though you can encode these configurations, you can count them as a Fourier integral, it's hard to use it. But Fourier analysis is always useful, okay? So even though the Fourier integral might not be that useful, techniques from Fourier analysis are always super useful, I would argue. And I'm just going to, in our next lecture, what I want to do is sort of exemplify some techniques you can get to work when you don't have access to orthogonality, or when orthogonality doesn't seem that useful. Physical space methods, we'll talk about Gowers norms, dual functions, decomposition theorems, and something called polynomial ergodic theory induction, or polynomial exhaustion technique. So these are methods which work involving Fourier analysis, but they don't require orthogonality. So the aim for our next lecture is basically, what do you do when the integral isn't that useful? And I want to give you a list of useful techniques. And the simplest example, the simplest application I could think of was a result of Bourgain and Chang showing that dense subsets of this finite field, Fp, contain this configuration. Now, this was known to ergodic theorists qualitatively, but Bourgain and Chang proved a very strong quantitative estimate for the maximum size of a subset of this finite field lacking this configuration. And we'll prove a similarly strong quantitative estimate, not as powerful as Bourgain and Chang's, but the quality is similar, it's comparable. And we'll do that by using a lot of these techniques. Okay, so that's all I wanted to say today. So now I'm going to stop the recording And if anyone's got any questions, feel free to unmute and ask them or put them in the chat. And I might be a little bit occupied while I try and stop these recordings and stop this streaming to YouTube.
Hi. I haven't checked the notes today, so I have one question.
Go for it.
Which step does not let you go for less than 5 variables in these steps?
Yeah, that's a great question. So yeah, it's this